Hey, welcome back to Math with Patrick. Today's September 19th, and we're solving problem 262 from the Daily Epsilon calendar. And the answer today, the answer for this x right here in the subscript, should be 19 because the answers to the problems in this calendar always match today's date. And it looks like we have a problem with like different base systems here. It's asking like 47 base what is equal to this number right here in binary. Like I guess I could call it like 1,010,011, but since this number is in binary, it's not actually 1,010,011. It's whatever this number is in binary. So let me at least write it on the page first. So one way to think about binary is that as we count up in binary, we can count up like we normally would, like 0, 1. But this number system only has 2 digits. So that's what this 2 kind of implies, is that we only have 2 digits that we're ever going to use. Or in other words, we're actually never going to see the digit 2 show up because we can only have 0 and 1. This might be a little bit weird, like why is base 2, why doesn't it have the number 2? Well, our numbers are in base 10, and it'd be really silly to have 10 as a digit. So maybe that makes sense why we'd never see a 2 in base 2. Anyways, so once I have 0 and 1, the only other thing I can do to increase the value of my number is to introduce another place value. And so the next number after 1 is 10 in binary. And so we can put little 2s underneath to just say that, hey, I'm counting in binary, and we can take a look-see at what's happening on the right side in base 10. So it's still 0 is still 0, 1 is still 1, but this number right here is secretly just a 2. Sorry, wait a sec. Yeah, no, that's just a 2. Because 3 looks like this in binary, and we can say that's 3 in base 10. And then now here, we've used up all of our digits, right? We have 0s and 1s. I have both 1s. That's the biggest digit I'll ever get. So the only other thing I can do to increase the value of my number is to introduce a new place value. And so this pattern keeps on going where we can kind of count up. Oops, that's supposed to be a 1 right here. So that was 5. This is 6. This is 7. And then this is now 8. And so if you notice some kind of pattern here with when we're kind of introducing a new place value, maybe you'll notice that all of our numbers that are of the form 1 and then zeros trailing after it are just powers of 2. Also, Quill just joined us right now. So we can assume that this number right here is going to be the same thing as 16 in base 10. And also, let's unpack base 10 for just a sec before we actually get back to the current problem at hand. In our base 10 system, this says that I have 1 10 and 6 1s. Like the number, 212 is going to be 2 100s plus 1 10 plus 2 1s. And then we can even write it in this exponential form just to have the number 10 show up in more places. We could even do 2 times 10 to the power of 0. And this idea of adding up like different powers of 10 with different coefficients at the front is going to be really important as we test out some values for x here. Because on the left side, this 47 in base x really just means I have 4 x's plus a 7, right? Because if this were in base 10 for a sec, that would just be 4 times 10, 40, plus 7. But in base x, I don't know what that base is supposed to be, but I do know that I'm going to multiply 4 x's together and add the 7. Technically, I could put those exponents back there, right? X to the power of 1, x to the power of 0, but those aren't really necessary to solve the problem. So at least for me, I think it would be easiest for me to think about this in terms of base 10 math, just because that's what I'm used to. So at least over here, I feel like I have some expression that'll help me solve for x. And then I do just want to convert this into some kind of base 10 number because that's just what I'm used to. So this 1 right here represents the number 1. This 1 represents the number 2. This is 4, 8, this is 16, this is 32, and this is 64. And so we can add up all of these values to figure out what this number is in base 10, just so we can think about it a bit more easily. 4x plus 7 is equal to, this right here is 80, that's a 3, so we have 83. Maybe I should put a little 10 right here to denote that I'm in base 10, but I think we can assume that if it's blank, it's a base 10 number. And now all we really need to do is subtract the 7. So we get 4x is equal to 76. And then now if we divide both sides by the 4, then we do get x is equal to 19. To do this in my head, I'm actually thinking of how many 4s I need to get to the number 80. This I can do in my head really quickly. And so if I have one fewer 4 on the left side, 1 fewer 4 than 80 is 76, then of course my answer is not 20, it's 19. 47 in its base 19 representation is the same thing as whatever this string of zeros and ones is in binary. And it happens to be, I guess, the base 10 number 83. Cool. So this right here is today's date, and that is the number we were solving for. And I think we are all done. So thank you for coming along and doing some different base arithmetic with me. And I'll see you tomorrow.